managing shear flows of dense suspensions with Bernard Grauwickel and Edward Becker. So, we live in a world filled with fluids. From the air we breathe to the water in our rivers and oceans, fluids are crucial to our everyday lives. However, we still don't understand many of their properties, such as the effect that occurs when a shear force is applied to a dense suspension. Understanding this effect is the main goal of our research. We are doing fundamental research, meaning that there are a wide variety of possible applications, yet the only direct benefit is improving scientific knowledge. One possible application is to predicting and controlling mudslides and debris flows. So we are using a computer simulation to model particles in a channel. We apply shear force to these particles by moving the walls in opposite directions. This causes the fluid near the channel walls to move at nearly the same velocity as the walls, while the fluid in the center has zero velocity. So when we increase the velocity of the channel walls by very little, this causes an abrupt increase in the mixture's viscosity. And this effect is called discontinuous shear thickening, and causes the fluid to flow easily when the velocity of the walls is low, but to become very thick when the walls are moving faster. And DST, or discontinuous shear thickening, or DST, occurs only in dense suspensions and does not occur in clear water flows, as seen in this graph of the viscosity of a clear water fluid and dense suspension as the wall velocity increases. Notice this abrupt increase in the viscosity of the dense suspension when the wall velocity is increased. This is DST. Also notice that the clear water flow or the viscosity of the clear water is fairly constant. And this suggests that DST is caused by some element of the particle's behavior, such as their clustering. And the main goal of our research is to understand the clustering behavior of the particles in the channel with moving walls that I just described. So this is an example. This is an example of our computer simulation. You can see that particles near the walls are moving more quickly, and the particles in the center are moving more slowly. And this simulation models about 2,000 particles over several hundred time steps and outputs the position of each particle at every time step. And you can imagine this is a huge amount of data. So my job is to write MATLAB programs to organize this data to quantitatively measure the particles' clustering behavior. So our main tool to organize this position data is the Bernard diagram, which is the collection of boundaries drawn around the volume closer to each particle than to any other. So for example, to create the Bernard diagram of these particles, you would first draw lines connecting each of the particles, and then you would draw the perpendicular bisector of every line. These bisectors form the boundaries of the Bernard cells. Using the Bernard diagram allows us to perform several calculations to quantitatively measure the particles' clustering behavior. Oh, and we apply the same concept of described with the Bernard diagram to our three-dimensional particles in the simulation to organize their position, as I said. So one such calculation that we can use from the Bernard diagram is the volume of the Bernard cells. And this gives us a measure of the particles clustering. So small volumes mean that the particles are tightly clustered together, while large volumes mean that the particles are farther apart. And then we graph the probability density function of these volumes to see the trend across all of the Bernard cells. And a probability density function, or PDF, is the probability of being in an interval divided by the length of that interval, and measures the relative likelihood of a volume having a certain value. So this is the PDF of the simulation of the volumes from the simulation compared to a random distribution, which we are using as our control case. And we found that the volumes in the simulation are much narrower and closer to, or the graph is narrower. The volumes are closer to the average than the random data, and this means that the distance between particles is about the same, and suggests that the particles are evenly dispersed. And because they're evenly dispersed, this leads us to believe that they are densely clustered, which forces them to pack evenly. To further analyze this volume data, we graph the volumes against the wall normal coordinate, or the coordinate perpendicular to the channel walls. And in this case, the volumes of the simulation are fairly constant vertically throughout the channel, which again suggests an even dispersion of the particles. And another calculation that we can perform from the largest horizontal dimension to the largest vertical dimension of each of the cells. And this measures the shape of the particle clusters. For example, if the vertical distance between particles is larger than the horizontal distance, then the aspect ratio would be less than 1. And if the horizontal distance is larger, the aspect ratio would be greater than 1. And if the horizontal and vertical distances are exactly the same, the aspect ratio would be 1. So this is the PDF of the aspect ratios of the simulation data, again compared to a random distribution. And the simulation data is closer to and more symmetrically centered on 1, which again suggests an even dispersion of the particles, because this means that the horizontal and vertical distances between particles are about the same, or closer to the same than the random distribution. So this again suggests an even dispersion of the particles. And to further analyze this aspect ratio, we measure the aspect ratios vertically throughout the channel using the wall normal coordinate, or graphing it against the wall normal coordinate. And we see that the aspect ratios are smaller, closer to the channel walls, and larger in the center of the channel. And this means that the vertical distances between particles are larger next to the channel walls and smaller in the center of the channel, which suggests that there's less particles moving quickly near the channel walls, and then a large concentration of particles flowing more slowly in the center of the channel. And this large cluster of particles in the center forces the particles to pack evenly, as we saw from the volume data and the other graph, the aspect ratio. So overall, this means that there is a layer of more clear fluid flowing quickly in the channel walls, and a dense cluster of particles flowing more slowly in the center of the channel. And this could possibly be one of the causes of DST, but a lot more research is needed to conclude this with more certainty. And that leads me to the next step, which is to perform calculations similar to the ones we did to measure the mixing of the particles. And then we'll run more simulations to varying the velocity of the channel walls and the number of particles in the channel to locate the threshold where DST occurs. And then once we've located this threshold, we'll compare the mixing and clustering of the particles on either side, and hopefully this will eliminate the cause of DST. Thank you, and thank you to everyone at CSEC and to the Gorman Scholar Program, and yeah, thank you.
What do you think causes them to cluster? Is it just that they're moving and there's curl in the fluid that makes them cluster in the center, or what?
Probably. Yeah, it's just that they're moving more slowly, so that I guess forces them to cluster. Whereas when they're moving quickly, they're more spread out just because they're moving faster, I guess.
Do you see if you move the walls fast enough, do you get turbulent flow in your?
Yes, but in what we're doing, we're keeping the velocity low enough that our flow is only laminar, because that's what we're looking at right now.
Okay.
Yeah.
Do you assume in your simulations there to be particle interactions or not? Friction or electrostatic forces?
Right now, the particle interactions are very low in the simulation, but that's another thing we need to look at in future research. Any other questions?
Could you just quickly explain again DST?
Okay.
And just, I guess...
So, discontinuous shear thickening is when a small increase in the wall velocity causes an abrupt increase in the mixture's viscosity. So here you can see that when at a certain point, we don't quite know where this is yet, that's what we're trying to find, when at a certain point in the velocity, the viscosity all of a sudden increases very sharply, and that's DST. That's abrupt increase right there.
Could it be just that they're packed now? I guess the particles are packing and that's what's causing that shift?
That's what we're thinking so far, but we need to do more research to conclude that with more certainty.
So how does mixing play a variable in the DST curve? Because you alluded to the fact that you're also studying the mixing behavior, but because it seems like it's pretty clear that clustering is a huge variable in the viscosity.
Well, I guess it's just another variable that we want to consider, because the mixing would be the particles moving around with respect to one another, so that's just another behavior that could
Wouldn't that decrease velocity if they're moving more? I mean, not velocity, viscosity.
Possibly, so that's another, either way it's a variable we need to consider.
What is the size of the individual particles in your model?
Right now all the particles are we're having all the particles be the same size, and they're fairly small. Anyway. Yeah?
Are you just looking at pure, you said you're working with water, is it just pure water, or are you accounting for different substances and impurities or things that...
Right now we're not, but that's another thing to look at.
Was this done in air fluid or liquid fluid?
Liquid fluid.
Okay.
But could be the same